This is the last topic. So the last topic, which is quite a big topic about integration, methods of integration. We have only a few, not spending too much time on it, and just getting some experience, getting a feel for integrals. And that's the picture at the top, supposed to illustrate the challenge of integration as opposed to differentiation. So no matter what class of elementary function you start with, you start integrating and you are outside of elementary. And then you increase the size, you learn more functions, and then you start to integrate those, and once again you have to expand on and on that class of functions that you're supposed to be able to handle. So creating new and new functions, so that's a challenge. So from that we're moving on to, so that's one example of a function right here, an important function that represents the normal distribution of quantities. One thing is that's the next topic, is what's so special about this function is that it looks like a bell curve. Okay, it is a bell curve, the bell curve. But what's interesting about it is that it is defined from negative infinity to infinity. As you can see, the domain is negative infinity to infinity. Okay, of this function e negative x squared. So this is y equal e negative x squared. Cannot be integrated by either substitution or by parts, so don't even try. But the interesting thing about it is that the origin under the graph is naturally infinite because the domain is infinite, but the area itself is not. Okay, so that's the next topic. That is the next topic of how to deal with infinite. First of all, why do we care? The example is once again the why do we care about infinities? Well, why do we care about infinite areas, which is kind of silly, but really it's not if you consider that distribution, which gives you the possibilities of infinite range of possibilities from negative infinity to infinity. That these are the values of x here represent the possibilities of a certain quantity runs between negative infinity to infinity, and the value of the function indicates the probability that this kind of this quantity takes this particular value. Okay, so this is how likely. So this is, I don't know, 3. Okay, so what's the likelihood that that quantity takes the value of 3, and the value of the function indicates how much. Okay, so that's why we care. And whenever we deal with quantities like that, we're talking about probabilities. The total probability has to add up to 1. Okay, so if it adds up to infinity, then we probably cannot. It's probably not something that we can handle as far as likelihood is concerned. So that's why we care. And but before we look into areas, into infinite areas, let me bring up something else. First, it is a particular integral of 1 of x. What's the integral of 1 of x dx?
ln absolute value of x.
ln absolute value of x. Any comments? Plus c. So that in the book, even the online homework requires that, or at least once or twice, that if you don't put plus c there, it's a mistake. But these things are worse than that. Here, the function is very particular, so it might appear that plus c can be kind of seen in a cavalier way, that you have a function, and then adding c, you have all the possible integrals, all the possible antiderivatives of the function 1 of x. Okay, so if you start with the function 1 of x, and logarithm looks like this. These functions will look like this, or let me do this. Logarithm of absolute value will look like this. Okay, ln absolute value of x, absolute value of x. So there is nothing wrong with it, but if we try to now implement plus c, remember what plus c is simply it is a shift of your function in the vertical direction. So this would be another one. I shift. So this is a shift, a vertical shift of my function ln absolute value of x. And then I could shift some more, and I could have as many as I like, but they are all identical. Another shift. So this is not, however, the answer. Not all the antiderivatives are here, and the reason is, so not all antiderivatives of 1 of x are here. Okay, so even though the rule applies, the rule states that if you found one, you have all. Okay, so you found one antiderivative. By shifting the antiderivative, you can find all the rest of the antiderivatives. That is the rule. There is, however, a caveat. You know what that caveat is? From calculus 1, possibly? So that's a version of the fundamental theorem of calculus, as a matter of fact. So if f capital is an antiderivative of f, then so is f plus c. Okay, so that's okay, but then there's the second part, is every all antiderivatives are found this way. There is an extra condition there that has to be satisfied, and that is when on any open interval. Okay, so the point is that we can only draw this conclusion whenever the function we're starting with is defined on an interval. 1 of x is not defined. Is defined on an interval, but it's not defined on negative infinity and infinity. So we are applying the theorem over here without the extra condition that, and that's why we haven't found all the possible antiderivatives, because if I look at there is a hole in the domain. There is a hole in the domain of 1 of x. It is x equals 0. Okay. Which is why the theorem does not apply to the whole real line negative infinity to infinity. It can only be applied separately to the left of 0 and to the right of 0. Okay, so which means that if I consider half of those curves, if I take one interval and then I found all the antiderivatives by shifting, okay, to the left of the y-axis. Okay, and then I look at what is to the right of the y-axis. Once again, I have found all the antiderivatives. However, if I want to combine them together, I do not combine them pairwise. I don't combine blue with blue. I don't combine red with red. I could combine, say, red with blue. This is what I mean. This is another antiderivative. So I'm combining red with blue. Okay, so that's another antiderivative that was not on the list. Why is it was not on the list? Yeah.
It's because it's a piecewise function.
It is a piecewise function, but the do you see how they don't match up? The what's to the left and to the right, it is matched up. The shift is different. To the left and to the right, the shift is different. So usually the rule applies, you write plus c and you have them all. But really, if there is a gap in the domain, you cannot get away with a single c. You'll have two c's. One to the left and one to the right. So the correct answer would be not ln x plus c, but rather like this. 1 of x is equal to ln x. Well, how about this? Plus c ln x plus 5 plus k, like this. Okay, x if x is less than 0, if x is larger than 0. So two separate shifts. You shift to the left one way, you shift to the right different way, and they might be misaligned like this. Okay, so for example, I could have put here, if I took the original function over here, I could put here 2, or I could put 3, but it cannot be simultaneously 2 and 3. But here, these two are independent constants, and they live separate lives, and I can have a function that is misaligned like this. Okay, so the point is, here's what if we ignore this caveat, and this amounts to a mistake unless you also add the extra restriction on every interval where the function 1 over x to define in the first place. So unless you add that extra condition, it is a mistake. And in y, what can happen is this. Let me try. What if I'm looking at a definite interval from -1 to 1 over x dx? Okay, so if I mindlessly apply that theorem, the fundamental theorem of calculus, I would have ln absolute value of x from -1 to 1, right? That's how we integrate. And then, well, ln of 1 minus ln of -1. What is it? Ln of absolute value of -1. The answer is 0. Okay, it is not that, so that's a mistake. So we applied the fundamental theorem of calculus, as we always do, but what we did not check that 1 over x is defined on the interval -1, 1, which it does not. Okay, so that's another way to look at this mistake, is that the fundamental theorem fails if your interval is not entirely covered. It does not cover the whole domain, or whatever, vice versa. If the domain is not does not contain this interval, so then that conclusion of the fundamental theorem cannot be overlooked or ignored, as I did here. So where did I make my mistake? This is a mistake. Okay, so to the left and to the right is different. I can apply the fundamental theorem for both the limits that are negative, or both of them are positive. That's fine. But when one is positive, one negative, I'm skipping over x equals 0, where the function is undefined, and the fundamental theorem fails under these circumstances. So the answer is not 0, and especially if we look at the picture, where that might suggest why. I'm plotting 1 over x. Okay. Now the region is between -1 and 1. Okay, so this is the region that I'm talking about. From -1 and 1. So what do you think the correct answer is? I mean, look at it. If you look at it superficially, you would see that there is a full symmetry, right? And what can we say about these two regions? Well, yeah, that I was driving at that. But it's so easy to make a mistake because they are identical. The regions are identical, and one is below the x-axis, above the other above the x-axis, and so under those circumstances they're supposed to cancel, and that's exactly what happened here. So the algebra that we have at the top is explained with this picture, but once again the picture is wrong. Why? Because I am unable to draw a region that is infinite. Okay, so it's going on and on, and there's really no way for us to understand what it is in the first place. The function is undefined and 0, so if we cannot really, we don't at this point know what it means for the area to be, for the region to be infinite. The region is infinite, it goes on and on, so even though, remember 1 over x has an asymptote, right? So x equals 0 is a vertical asymptote of 1 over x. Okay, so it means that the two graphs get together, but they're virtually merged, but they're not literally merged. So, which means that there will be always a gap. If you zoom in, it doesn't matter how close they look. You zoom in, and you will see a gap. So the region goes on indefinitely in both directions, here as well as there, down too. So in other words, if you carry out this computation that we started with, you are skipping over that difficulty and producing a result that is not not to rely on, and in fact it is incorrect. So the answer is yes. No.
What if they're not identical?
Well, they are. In this particular case, they are.
But what if you tried from like
Yeah.
-1 to +3?
Okay, so well, you would still end up with a number, right?
Right.
So like if I have integral from -1 to 3, 1 over x dx, and once again, if I ignore the restrictions on the fundamental theorem, I would end up still ln absolute value of x between -1 and 3, and I have ln of 3 minus ln of 1, and so the answer is ln of 3. Hold on a second. It's not ln of 1. Hold on, that's not right. Well, let's just leave it like this. So it's a number. ln of 3, ln of 1, two numbers, subtract these two, have a number. So we once again we are hiding that the problem that we overlooked over here. That problem. The fundamental theorem allows us to, from the interval from -1 to 1, skip to only the endpoints of the interval. And all we care about is, if you find the antiderivative, all we care about is two of its values at -1 and 1 or -1 and 3, and whatever is happening in between doesn't matter anymore. But that transition only is possible when there are no holes in the domain. There's a hole in the domain, and we end up with a computation which simply is incorrect. And we see the difficulty. If we look closer, the difficulty turns out to be that the region is infinite, and we simply do not know how to handle it. If you remember from Calculus 1, the functions are called. You can only define the definite integral a b f(x) dx. The assumption is f is defined on the whole interval ab. So what happens when it's undefined somewhere in the middle? We simply cannot rely on Calculus 1. We have to start over. Okay, so as you can see, we see already two examples of infinite regions, which may or may not have infinite areas, and that's what we're going to be looking into how to first of all figure out what it is, what's the meaning of the area of an infinite region to begin with, and then secondly determine what it might be. And we'll have two examples over here. This one, the region is infinite, but the area is finite. Okay, that area over there is 1. However, in this particular case, as we're going to see, this area is infinite. Not only the region is infinite, the area is infinite. Okay, first of all, before any kind of difficulty come into play, let's just look at a simple example. F of x is equal to 1. Say from 0 to 1. So this is my graph, y equal 1. Okay? I'm sorry, not from 0 to 1. The interesting question is, what if from 0 to infinity? Okay, so this is my graph right here. This is my graph. And then we're looking at the domain. This is the domain. It is infinite now. So the region itself is this. So what do you think about this region? It's like a band, and it starts at on the x-axis, on the y-axis right here, but it goes on to infinity. So the region is infinite to begin with, right? It's an infinite band. Any doubts about that? It is certainly infinite from the definition, because these two will never meet. Two parallel lines never intersect, right? So they will keep going. It is indeed an infinite band. Now, but what about the area? The area of this band.
It's finite.
What do you think?
If you plug in x values, you can surely figure out the area.
You should. So let's figure out the area, or unless you can tell from the look of it. Well, we'll try to do it the calculus way, but what does common sense tell you about the area? It is infinite. The area is infinite. You can think about it as, how much material does it have? It's like an infinite well. How much water does an infinite well contain? Well, it contains an infinite amount of water. The only chance that it's not infinite if it starts to narrow down. If it starts to narrow down, then maybe it narrows down so quickly that, in fact, it can be filled with only finite amount of water. But if it is not narrowing down, well, there you go. It has got to be infinite. So in other words, what we're saying here, and let me try to have this written up at least. So integral 1 dx from 0 to infinity is infinity. Okay, that's what we want to have at the end of the day. We want to have a function over here, just the usual function as long as it's defined on some infinite interval. And then we have two limits, one which might be infinite. Okay, and then we want to figure out what the answer is. It might be infinite, as this one says, but it doesn't have to be infinite every time. So how do we determine that? And the idea is you don't want to start from scratch. Scratch being Riemann sums. Remember Riemann sums. So Riemann sums, you take an integral in finite interval, and then divide it into smaller pieces, and then build those bars. Remember that. Okay, so that's not going to work for us because we don't want to start from scratch. Besides, if we take the infinite region, infinite domain, then there will be infinitely many bars. And that is just the complexity we don't want to deal with. The answer is very simple. We just expand. We solve the problem on a finite interval first, and then see what happens. So this is the idea. Consider integral from 0 to, say, b, 1 dx for all b. Okay? For all b. So in calculus 1, we did Riemann sums on interval ab, so the lower limit is fixed, upper limit is fixed, and at the end we have either the number or something nasty possibly, but most of the time it would be just a number. But suppose the function is well behaved, so we can always figure out its Riemann integral over a finite interval. Okay, so the function is 1, so it's a really simple function. In fact, we can go ahead and write what this is. Integral from 0 to 1 dx. This is entirely within calculus 1. What's the answer? From 0 to b, 1 dx. No, x, indefinite interval is x, and then what? X from 0 to b. It's just b, right? So, and now this is the idea is, and now we just take, this is b, this is my area, this area is b, okay, and then what do? Let b go to infinity. And see what happens to the area. So the b, the upper limit, b is the upper limit. We let it go to infinity, and just we compute the limit of the areas, right? So compute the limit of this as b goes to infinity. Well, b goes to infinity. So we just right away have demonstrated that indeed the areas will go to infinity. So this statement has been explained. So we're saying that the area is infinite. In what sense? Well, in this sense, we cover this area a little, but it's like exhaustion that we did previously a little bit. Exhaustion of the area from the inside, and see what happens at the limit. So the exhaustion that I just maybe remind you of something from the past, how you can compute the area of the circle from, you approximate it from inside by regular polygons. You compute the areas of those polygons, and then take the limit of those, and that limit will give you the area of the circle. Okay, we did pretty much the same thing on the first day of classes. Okay, and we're doing a similar thing. So once again, we have the region, which happens to be infinite this time, and we try to exhaust it from inside out, and computing area as we do it, and we see if area goes anywhere. So if it goes anywhere, then we're good. If not, we're in trouble. In fact, so since we started with 10x, let's do example with 10x. So let's apply this plan. So take 10x, f of x equal 10x. I will be looking at this at the other half of the graph. So the graph is 10x, and I will be looking at this part, an infinite part, which, by the way, remember that the issue we started with was the opposite part, what's left, rather than so the one that goes into infinity up. This is what we started with, this one. But you can see that because of the symmetry, these two are pretty much the same. Like these two regions are identical. This one and that one. So it doesn't really matter. So these two yellow regions are identical, and they're certainly, if we solve the problem for one, we solve for the other as well. So this is what we're trying to figure out. So the question becomes, what is this area? Okay. Okay, so once again, this is y equal 1x. Okay, so we're looking at the yellow area that expands to infinity on the right, and we want to find its area. We know already what to do. We compute. Well, let me point out what is that we are trying to accomplish first with the pictures. So we put a b here. That's the key step. Is this is 1 and this is b, and we start with this region. So the region that we start with will be variable but finite. So it will vary in width, but at every moment it will be finite. So we entirely will do calculus 1. So 1 and b. So find this for every b. So that's the plan. And we know what it is. We do it by integration. So the area, or the integral, the area of this is integral from 1 to b, 1 of x dx. Yeah. Okay, so is it clear what has happened here? So we're trying to figure out infinity regions, but we do it by understanding finite regions. So we cut that infinite tail. We don't want to. It's hard to deal with infinity just like that. So we usually handle infinity with limits. So before we get to limits, what is that we have to deal with? We have to deal with this finite area over here, cut out of the infinite area. Okay. And then what is it? It is equal to integral, as we know, of the function from one limit to the other. Okay? So what do we do next? How do we find the integral? One of x dx. We already did it by differentiation a minute ago. So what is it equal to?
Natural log.
Natural log, yeah.
Absolute value.
I don't need absolute value, right? So it will be from 1 to b. That's it, right? There you go. Okay, so I substitute the fundamental theorem every time. Works out. It works out because we stay to the right of 0. So that problem we had early on, we're not facing, because we're sticking the hole in the domain is here somewhere, so we don't care about it. So it will be simply ln b minus ln 1, right? Okay, so what's next? So for every b, we know what the region is, the area of the region is. That's what it is. Now, what?
Riemann sums.
No, we don't. We don't really want to do Riemann sums. That's the way to get around Riemann sums. It's the way to rely on the integral, on the Riemann integral, and whatever we know about how to find those. So as you can see, we have found the area under the graph, part of the area under the graph from 1 to b. So as you can see, we found this. Whatever b is, it could be 1, it could be 2, and it could be 3, and so on, all the way to infinity. So what's the next step?
We take the limit of the function as b goes.
Right. Take the limit of this as b goes to infinity. Okay, so all we have to do now is remember a little bit about limits, and what is it? Where does L and B go when B goes to infinity?
0.
No. Remember the graph of the logarithm? We plotted it just a few minutes ago. This is what? It goes to infinity. These are the graphs of the logarithm, and they go to infinity. That's the thing about logarithm. Even though it slows down, but it doesn't flatten out. It doesn't do this. It keeps going up. So the answer is indeed infinity. So the conclusion is, as we suspected. So the total area under the graph is infinite. Okay, so infinite region, infinite area. That pretty much the intuition tells you that should always be the case, but it's not. So the next example is to show when, under what circumstances you have an infinite area, an infinite region with finite area. Well, apparently, as you can see, the graph here, even though it is narrowing down, look at it, it's narrowing down pretty quickly, but it's not narrowing down fast enough. You still add, every time you move b to the right, you add too much to the total area, so that it still goes to infinity. Okay, so what should we try in order to have a chance of having finite area? So we picked the graph of y and 1 over x. What else could we pick? Well, what do we want from a function in order to make its graph narrow down faster and faster than this? So 1 over x is not fast enough. What do you pick?
X squared.
1 over x squared. I don't see why not. So that would be an idea to put a square over here. What's going to happen? What is the integral of 1 over x squared? Well, let's start over. So what we want is faster decline. So try f of x is equal to 1 over x squared. It declines faster, right? 1 over x squared declines faster. Okay? In fact, you can think in terms of L'Hopital's rule to see that one is faster than the other. Okay, so then we're looking at the integral from 1 to b, 1 over x squared dx, to how do we integrate 1 over x squared? What kind of function is this? What? Well, the function is, what kind of function is this? What?
Is it rational?
It is rational, but it's simpler than that. How do I can rewrite it? 1 over x squared?
X to the negative
x negative 2, which makes it a power function, and we have a power formula, right? Okay, so what's the power formula? No, the integral. So derivative, that power goes down, integral power goes up. So it will be, what's the power? X power negative 1. 1 over negative 1, once again. Right, so you can check it out if you differentiate negative 1, that's what you're going to get. And it's from 1 to b, once again. And so if we continue on with this computation, we'll have negative b negative 1. What is it? Plus 1. Okay, so once again, a faster declining function. Maybe let me make. Whoops, it's too fast. Make that point. A declining function like this, faster than 1 over x. Okay, we're still looking at from negative 1 to infinity. So 1 to infinity. So this is the region we're interested in. We picked a b here somewhere. A random number, and then naturally what the next step is, let b go to infinity. Okay, so what's the limit? As b goes to infinity? It goes to 1. So b negative 1, simply 1 over b. So this one goes to 0, and this goes to 1. Okay, so the answer is 1. Okay, so we have demonstrated that the area under this infinite region, as you can see, has finite area. So infinite region, yet finite area. It is in fact equal to 1. Okay. So, any questions about how we did it? So these are the two typical situations, and the functions are very similar. The only difference is that one is declining faster than the other. Okay, and one gives you infinite area. They look very, very much the same. One gives you infinite area, 1 over x. 1 over x gives you infinite area. 1 over x squared gives you finite area. Well, you want to guess what happens in between 1 over x and 1 over x squared? What if it's 1 over x 3/2? Finite or infinite? Yeah, it is finite. Because, can you explain quickly why?
Because it's the same thing as power.
It is, once again, a power function, right? And the power will be simply negative 3/2. Negative 3/2 goes up by 1. It will be negative 1/2. And the limit will be still 0. That similar expression over here, and it will be 0 again. So anything less than 1 will be, or rather anything larger than 1 in the denominator over here, will give you a finite area. But you can guess that if it is less than, say, 1 over square root of x, will be infinite. So 1 over x 3/2, x 3/2 finite. 3/2 to 1 over x 4/5, and so on, all of them will give you a finite area because it gets thinner and thinner and thinner, and therefore all of these areas will be infinite. On the other hand, if from 1 over x you proceed to functions that decline slower, such as 1 over x, all of them will give you infinite areas. So it's like a comparison property of integrals. Remember, so one function larger than the other, then so are their integrals. Okay, so well, before we look at more complex examples, what is the function that declines faster than all of these? 1 over x squared, 1 over x cubed, 1 over x fourth. Keep going. Is there anything declining faster than those? So it declines faster than 1 over x squared, 1 over x cubed. Looks the same, kind of. There, no such thing, no. No, 1 over x squared, 1 over x cubed. 1 to the exponential function, yeah. So f of x is e negative x. Okay, so it declines faster. So the exponential growth faster than any polynomial function. Then you flip it over, it declines. Exponential decay is faster than decay or decline of any other polynomial function. So e to the negative x, and once again we can now maybe write out in a more in one line. So I'll go for integral from say 1 to infinity e negative x dx. Once again, a simple function that we can handle, but we do not jump to conclusions right away. We go through the limits. So we understand these limits. They're called improper integrals. We understand them through limits in no other way. So it will be a limit. B goes to infinity. Integral from 1 to b e negative x dx. Okay? So once again, new problem of infinite domains. So this is the domain here of integration is infinite. We have reduced it to a finite domain, which we know how to handle. And we handle the infinity with limits. So the limit is a key idea, which is, as you can see, is applicable to so many places. It's starting with derivative, then the integral itself, the asymptotes, and now even this. Okay, so the limits b goes to infinity, and we just continue the computation. And okay, so we leave the limit alone for the time being and just compute the integral as if b is fixed but unspecified. Okay, so well now let's check how well you integrate e negative x. What's the antiderivative? E negative x integral dx. Well, if you don't remember the answer, and maybe better if it's fine if you don't, then you have to think of a method of solving it. What's the method? Well, there's a composition here. You see a composition? You substitute, right? So you first x, then negative x, then exponential function. That's the composition. So whenever the intermediate stop is your new variable u. So we say u equal negative x, du is equal to negative dx. Okay, and then the substitution then is completed, and we have integral from e u negative du, right? And we have an integral with respect to u. We integrate it. We will pull negative sign out, right? The integral is eu du, negative eu, okay, or negative e negative x plus c. Okay, and that's as you can see, either you do it this way, or it's also okay to just remember the answer, because after all, this is differentiation, reverse differentiation. You know what happens when you differentiate a function with a negative sign. It will nothing more than just a negative sign in the front of your function. So it's up to you, but certainly you can easily verify the answer that way. So that is our antiderivative. So let me continue on here with my limit. So the integral is taken care of, right? And so that limit at the top right, I have then limit b goes to infinity, negative e negative x from 1 to b. Okay, that is the fundamental theorem. And I still have the limit. I substitute, and I have e, negative b, plus e, negative 1. Well, you can see that it will get, at the very least, it's going to be finite, right? So b goes to infinity. What's happening? What's happening to the first term there? B goes to infinity. Where does this go? What? It goes to 0, and the other one? It does what? Yeah, it doesn't go anywhere. It is already constant. It does not depend on b. So that's the answer. 1 or e is the area under the graph of the exponential function. Once again, infinite area. Once again, so the origin that you see on the picture is infinite, expands indefinitely to the right, but its area is finite, and that's the answer. Okay, so we convene tomorrow.